Hi, I'm Mike Fairborn, Chief Meteorologist here at WCCO TV. Few places on Earth get the variety of weather, thunderstorms, blizzards, tornadoes that we get here in the upper Midwest. It sure keeps life interesting. But now, research into weather phenomena like global warming and ozone depletion reveals that human activity all over the Earth might be changing the weather, dramatically affecting plant and animal communities which can't adapt to big changes in their environments. So, the first 5 stories in our forecast look at the forces that make the weather, and the last 5 look at climate, weather patterns over centuries. We usually think the surface of the Earth is under our feet, but actually it's above our heads. We live at the bottom of an ocean that covers the Earth like a blanket. The atmosphere, the blanket of air that surrounds our planet, is filled with dramatic displays of nature's awesome power. But there's more to the atmosphere than weather. All the planets have an atmosphere, but this atmosphere that we live in is pretty unique, really, throughout all the planets in the solar system. Our atmosphere contains the basic building blocks of life as we know it: nitrogen, oxygen, hydrogen, and carbon. Our atmosphere, compared to the Earth itself, is very thin, thinner than the skin on an apple, but it still has layers, defined by height and temperature. The bottom layer, the air, the layer that contains the life support systems for us, most of the water, most of the oxygen, the troposphere, that's the thing that we live in. The next layer above is called the stratosphere. It has most of the ozone, the oxygen molecule that shields us from the sun's harmful ultraviolet radiation. The mesosphere is above that, between 30 and 50 miles above the Earth. It has rare gases like neon and argon that create the northern lights. And the thermosphere, even though the air is much less dense and the temperature is increasing, is really kind of, I guess, our first line of defense against the bombardment of the solar radiation. When you think about this blanket of air that we have out here that we live in is so fragile. It's just so delicately balanced. The gases that we have to have for support of life, and we start to mess around with those. We start to disrupt that balance, and we don't know what kind of changes we affect in not just in the weather, but in our ability to sustain life on this planet. Plant communities and the animals that depend on them can and do adapt to changes in the atmosphere if they take centuries to occur. But now we humans are changing the atmosphere so quickly that nature might not be able to adapt. Most of these changes are taking place in the lowest layers of the Earth's atmosphere, the troposphere, where we live and where weather happens. The stratosphere is the next layer up, where ozone is found. Then comes the mesosphere, where the northern lights occur. And finally the thermosphere, the boundary with space. Most of the Earth's air blanket is nitrogen gas, about 78%. Oxygen makes up 21%, and the remaining 1% has everything else: argon, helium, carbon dioxide, and other gases. And it's changes in this 1%, especially the level of carbon dioxide, that scientists are watching closely. But what keeps these elements and compounds mixed together? It's the wind, you say? But what makes the air in the atmosphere move, and why does the wind blow? Sailors love the wind, air in motion. When it fills the sail, the boat moves. The only sounds are the waves, an occasional bird, and the wind. But wait a minute, why does the wind blow? What makes the air move?
Probably the most important thing is the sun's rays, radiation from the sun. It's shortwave radiation that enters the atmosphere and heats the atmosphere, and it heats different parts of the atmosphere differently.
The shape of the Earth makes a large difference in heating between the polar regions and the equator. Simplified, these temperature differences create pressure differences, since heated air rises and cooled air sinks. As the Earth rotates, these large masses of air move from areas of high pressure toward areas of low pressure.
In the upper levels of the atmosphere, the radiation from the sun near the equator causes high pressure, and air flows from that high pressure downhill toward low pressure near the poles. But because of the rotation of the Earth, it gives a little turn from out of the west, and those are the westerlies.
These westerly winds carry our weather every day. The jet stream, a river of air high in the troposphere, is part of the westerlies and helps guide the weather on the ground.
Think of the atmosphere as an ocean of air. It's constantly moving, and the strongest current in that ocean is the jet stream, and the jet stream is what determines what type of weather we get, and it also helps determine the storm track for storms.
But when the storms move past, clear skies usually take their place. Blue skies and sunshine. Perfect weather for a ride on an ice boat. Like waves in the ocean of air, the prevailing westerly winds wash over us, with each wave bringing changes in our weather. Almost every night on the weathercast, you hear me refer to the weather conditions to the west, in North and South Dakota. That's because their weather today is usually our weather tomorrow. The westerlies see to that. Do you remember what makes them blow? Can you name the parts of what we meteorologists call the general circulation of the atmosphere? They are solar radiation, which heats the planet unevenly; the Earth's rotation, which helps create the prevailing westerlies, the winds that blow from the west; and the jet stream, the steering currents in the upper levels of the atmosphere. People love to talk about the weather, and probably always have. So there are lots of sayings and proverbs about it. One of my favorites, which fits the northern Great Plains especially well, is, "If you don't like the weather, just wait a few minutes." It fits because our region is halfway between the hot equator and the cold North Pole, in the middle of a continent, far from the moderating effects of the ocean. So our weather goes to extremes, through the seasons, even day to day, and sometimes hour by hour. We can see these changes every day by watching the clouds, which form as the ocean of air around us swirls and mixes. Our next story looks at how clouds form and what they're made of. A heavy, wet snow, like any precipitation, falls out of clouds that form in the troposphere, the lowest level of the atmosphere. Clouds will form again as the winds keep blowing and more moisture evaporates. There are many types of clouds. Most have long names. High-altitude clouds, the cirrus family, are made of ice.
The temperatures in the upper atmosphere are quite cold to form those ice crystals. And that's the time, too, that you get a lot of vapor trails in the sky when the jets go over. There are the middle range clouds called the alto clouds, kind of like the alto voice, I suppose, in the middle of the range of voices. And those are made up of ice and water. Then you have the lower range of clouds, the stratus clouds, that are just made up of water.
In the warm air of summer, heap clouds form. They can cover all the height ranges.
And then you have what's sometimes called the popcorn clouds of a summer day, the little cumulus clouds that just dot across the sky, and the big billowing summer clouds of the cumulus. There is a beauty, there's a majesty in the clouds. If that continues to develop into a thunderstorm, into the nimbocumulus variety, one of the cloud classifications, you know that probably thunderstorms have developed, and then out of those you could get serious weather. Tornadoes could develop and hail.
As the clouds appear and change, so does the weather.
And really it's like a canvas in the sky to see the clouds, and you can look at the canvas and tell a lot about the weather.
The variety of clouds we see in the upper Midwest mirrors the extremes of weather we have. But they fall into three main categories. Do you remember what these cloud types are usually made of? The worksheet answers are ice. That's what the high clouds, cirro-type clouds, are made of. The mid-altitude clouds, alto-type clouds, are made of ice and water. And the low-level clouds, strato-type clouds, are made of water. All of us, young and old, have watched the canvas of clouds and even imagined animal shapes forming. In our next story, we're going to take sky watching another step to see what watching the sky in lots of places all over the earth can tell us about the weather. In the last few decades, meteorologists, those of us who watch the sky for a living, have developed some valuable tools for sky watching.
Every day I come out at 5 p.m. and I take the temperature readings for the last 24 hours. I read the maximum and the minimum and the present temperature. and I record any precipitation that's occurred during that period of time.
Jerome Stoffel's family in Farmington has been watching the sky and keeping weather records since 1888, longer than anyone else in Minnesota.
This over here that we have on the side is a little roof weather station.
Here at the Weather Center, we watch the sky and keep records too. And we get observation data from sites all over the country.
By taking observations of temperature and air pressure and wind and sky cover at a lot of different locations and using them all at one time, we can tell what weather patterns are like over a large area of the country. One of the cameras is what we call an infrared camera, and that senses difference in temperature. What Weather Satellite does for us is it's in orbit 22,000 miles above the Earth, and it takes a picture every half an hour that gives us an idea of what cloud patterns look like across the entire country, or for that matter, the entire world. Over here we have our Doppler radar. This is a new radar that we got here at Channel 4 last
WCCO's Doppler radar, besides detecting precipitation in our area, also lets us see the wind to identify dangerous storms before they strike.
What it actually is a beam of microwave energy similar to your microwave oven that is sent out from a radar site and that bounces back off of precipitation. And by the strength of the signal with which it bounces back, we can tell how hard it is raining or snowing and also pinpoint exactly where that's happening.
Benjamin Franklin was one of the first Americans to study weather scientifically. In fact, he was the first person to speculate about the effect of volcanoes on the atmosphere. Today, observing changes in the sky and clouds like Franklin did is still one of the most important ways we keep track of the weather. Two 20th century inventions, radar, which lets us see precipitation, and satellites, which take pictures of clouds, help us watch the sky from new vantage points. So, how do we meteorologists take all the information these tools give us and predict what's going to happen, create a forecast? Well, our next story reveals it's a combination of science and art. When cumulus clouds begin to thicken and it starts to get dark, you can tell it's going to rain. But how could meteorologists have predicted it would happen 2 days earlier? Well, the first thing we do when we start to put together a forecast is to take a snapshot of what's going on. We want to know what is happening out there right now. That means a computer-generated map of the atmosphere that shows the location of cold and warm masses of air, high and low pressure areas. And then we want to know how those high pressure areas and low pressure areas are going to move with time. When these large masses of air rub against each other, pushed by the jet stream in the westerlies, the collision creates a front. Usually this is where precipitation occurs, strong, hard rain or snow that ends quite quickly with a cold front, more gradual, long-lasting rain or snow with a warm front. The daily progress of warm and cold fronts across the planet is weather. The ebb and flow of weather over the centuries is called climate. It's the history of weather, and people have been keeping accurate weather history for 200 years, but nature has been keeping records longer. Scientists have measured the gases of the ancient atmosphere in air bubbles trapped deep in the ice of Greenland's glaciers. From these historical and natural records, scientists have created computer models of the atmosphere over time. These models allow them to forecast the climate, and when they compute the ways human activity is changing the atmosphere, some of their forecasts are sounding alarms. Data collected since 1957 in Hawaii, for example, shows that we're adding more carbon dioxide to the atmosphere every year as we burn fossil fuels like oil and coal. During the last century, it's up more than 20%. What tools are scientists using to investigate these changes and make long-range forecasts, climate forecasts? Well, they use models of the atmosphere designed on computers. They retrieve the ancient atmosphere by drilling ice cores into glaciers, and they research the records of weather history. So, we've seen how the atmosphere works to create our daily weather. Now we turn to climate, weather over centuries. During the 1980s, we had 5 of the hottest years on record, and we burned more of our fossil fuel savings account than ever before. But how are the two connected? Most of us call it global warming. Our next story looks at whether our planet is getting warmer and warmer.
Essentially what we're doing is we're living in a great uncontrolled experiment right now. We're dumping things into the atmosphere
and changing the balance of its elementary gases, especially carbon dioxide. It's an experiment not in a laboratory or computer, but on our own planet.
Emissions from automobiles are probably the single most important thing, because not only do they emit a lot of carbon dioxide, they also emit methane and nitrous oxides, or NOx.
Even animals add to the greenhouse effect by producing methane gas. The greenhouse effect refers to the ability of these gases to trap heat.
Sunlight comes down through the atmosphere of the Earth and it hits the surface. A certain amount of it is absorbed by the Earth and the rest is reflected. And some of the radiation goes back up into the air and escapes to space, but some is also trapped by certain gases that we call greenhouse gases.
Life, as we now know it, depends on the warming effect of these gases. But the increase in these gases from burning fossil fuels in our cars and electric power plants will increase the heat trapping and may warm the climate. So, scientists use computer models to try to figure out how the climate might change.
On the basis of those, they have predicted that the temperatures across the Earth, depending on where you are, it varies somewhat, should increase by a number of degrees over the next 100 years or so.
But even a change of a few degrees will be much faster than most of nature can adapt to.
Clearly, we can't wait until the greenhouse effect is upon us, because it's going to cost a lot more to deal with the results of that than it would by trying to take some sort of realistic actions now. Can I talk my parents into using less water or using the car less often? Can I work into carpooling somehow? Things like that. Those are all important ways that we can help now.
You might call it a no-regrets approach to the unknowns about global warming, changing now before it's too late. Many countries are taking dramatic steps to change the way they live now. Holland plans to get 20% of its energy from wind power by the year 2000. Do you remember what produces greenhouse gases? The worksheet answers are fossil fuels. Burning them in our cars and power plants produces CO2, carbon dioxide. Animals produce methane gas, and cars produce nitrous oxide and other nitrogen compounds known as NOx. Most of us know about acid rain and snow, but now other more dangerous chemicals are showing up in precipitation. Even pesticides from cotton fields have been found in Lake Superior. More and more, the chemicals we use in our factories and homes are being found in the atmosphere, making the clouds toxic. Snow and rain wash chemical compounds out of the air, so precipitation is usually a little acidic. But the way we burn and use fossil fuels adds more than extra acidity to the atmosphere. Some of society's most hazardous chemicals are put into the air too.
What happens is the companies dump toxic chemicals into the air and they are transferred back down into our lakes and onto our land by the weather systems that are at play.
Some of these chemicals are heavy metals, like mercury, from coal burned in power plants. When the mercury falls or is washed out of the air, it accumulates in the food chain. And now, fish from some lakes aren't safe to eat more than once a month.
One of the biggest problems in Minnesota with toxic chemicals being dumped in the air is with solvents. A lot of the products that are made require painting and require different coatings and also have to be cleaned.
During manufacturing processes, most of these solvents evaporate, but that doesn't mean they disappear. They mix with the other gases in the atmosphere and sometimes form new pollutants.
One of the most troubling air toxins that we're dealing with right now is dioxin.
This cancer-causing chemical is a byproduct of garbage incineration and the bleaching process in paper mills that makes paper white.
What the solution to the problem is for companies to sit down and look at their process and figure out what they can do to change that process so that they can create a product that's just as good but doesn't pollute.
In 1990, industries in Minnesota reversed the trend of rising toxic emissions. Even so, they released almost 70 million pounds of toxic chemicals into the air. Nationwide, more than 2 billion pounds went into our air. Can you name some of the pollutants that make clouds toxic? They are solvents, which may evaporate after they're used but don't disappear, heavy metals, which are released when coal and garbage are burned, and dioxins, byproducts of burning garbage and bleaching paper. Another class of common chemicals is an even more serious threat to the atmosphere. It's a greenhouse gas, it's destroying the ozone layer of the atmosphere, and it's as common as an air conditioner. It's the chlorofluorocarbons, or CFCs for short. Their ability to destroy ozone was first discovered in an unlikely place, the skies over Antarctica. The ice glaciers of Antarctica are home to some of nature's most unusual animals, the humpback whale, the Weddell seal, and several species of penguins. It's also home to an unusual atmosphere, ice crystal clouds in the stratosphere. But the ozone in these clouds is being destroyed by chemicals we use thousands of miles away.
So if you use these chemicals at the surface, they eventually make their way to the stratosphere, they're broken apart, and in the set of reactions, the chemical reactions in the stratosphere, they essentially act to destroy the ozone layer, that where 90% of all the ozone is.
When spring comes to Antarctica, the ozone layer gets thinner by 50%. It's alarming because this layer protects life on Earth from the harmful effects of the sun's ultraviolet rays.
If I'm exposed to ultraviolet radiation, I have an increased chance of getting skin cancer. And then there are a series of effects, possible effects on forests and crops. If you expose plant life to increased levels of ultraviolet radiation, the plants suffer. Productivity goes way down.
At the same time we're destroying ozone in the stratosphere, we're creating ozone in the troposphere, at the surface. It's smog.
As a result of driving our automobiles, we release a compound out of the tailpipe called carbon monoxide, or also other compounds which are called hydrocarbons. And in the presence of sunlight, they react with oxygen to form ozone.
And breathing ozone is harmful to people. It contributes to lung damage and disease, and has a similar effect on the lungs of plants. Annual crop damage from surface ozone costs billions of dollars. Driving cars less and keeping them tuned up will help reduce surface ozone pollution. But what about keeping ozone in the stratosphere?
Air conditioners and automobiles are probably the single leakiest source of chlorofluorocarbons that we have.
So when you do have it checked, make sure your service station captures and recycles the CFCs. Most refrigeration and air conditioning systems use CFCs, so be sure to recycle their CFCs too. Of course, if a leak is chronic, be sure it's fixed, and you can now find non-CFC alternatives for many situations. So what are the dangers of ozone depletion and ozone pollution? Too little and too much ozone? The answers for the worksheet are cancer. Skin is more vulnerable when ozone is depleted. Trees, crops, and other plants suffer damage from both too little ozone and too much ozone. And people who breathe too much ozone may get lung diseases. Global warming, toxic air pollution, ozone depletion, these are big problems. But what can we do to solve them and reduce, even eliminate the climate-changing gases we produce? For most of the Industrial Revolution, we've treated the atmosphere as a convenient dump. Now we're loading it up so fast it can't clean itself. So we'll have to design pollution out of our society. Among industrial designers and engineers, it's called closing the loop.
We're looking at processing right now.
Okay.
And this will serve as the interface to the current existing conveyor layout.
Environmental engineers at the IBM plant in Rochester are installing another computer parts cleaning system, one that doesn't use ozone-destroying CFCs.
IBM realized that we needed to eliminate the use of CFCs. The company made a commitment to eliminate CFCs by the end of 1993.
Getting rid of CFCs and using a soap and water-based cleaning process will help preserve the ozone layer and is actually saving IBM money.
The problem is that when you use chemicals, you also have to plan for their disposal or treatment. And we would like to redesign our processes more efficiently to either minimize the amount of chemicals used or avoid the waste altogether.
Other companies are making progress closing the loop, designing pollution out of their manufacturing processes. The 3M plant in Hutchinson used to dump millions of pounds of toxic chemicals into the air. Now it captures most of these chemicals at the end of the process to use them again.
There's a real benefit for us. It makes us a lot more competitive, and we're doing a good job for the environment. It's kind of a win-win situation for everybody, really.
In our homes, we can substitute energy-efficient products for less efficient ones. Compact fluorescent bulbs use about 1/4 as much energy as incandescent ones. Developing alternative energy resources like solar power could help solve many air pollution problems because burning fossil fuels produces most of the gases that are changing the atmosphere. Even wind power can provide some of our electricity needs. Using alternative energy doesn't mean going without.
One thing people have to realize is that these are complex problems, and it can't be done overnight. It's a long-term process that takes time, and that we all have to work together to accomplish that.
The changes required for our society to stop polluting the atmosphere are enormous, so we'd better get started. Can you list some of the things we can do? We can use alternative energy resources like solar and wind power. We can substitute energy-efficient products for less efficient ones, and we can redesign industrial processes to prevent pollution in the first place. Our series concludes with a look at what we can do individually to prevent air pollution, to reduce our own contributions to the amount of climate-changing gases we use.
We get out and find some just simple, wonderful joys in being out together in the woods.
Learning how to live a less polluting lifestyle can be a challenge, but you can still have fun doing it.
Well, I think there's a lot that each of us can do to reduce the amount of climate-changing gases. And of course, the biggest thing is to save energy. I think when kids look at what they purchase, or their moms or their dads purchase, look for things that don't take as much energy. Maybe things that were made locally, so they didn't take so much energy to transport them.
Polluting less means living within a carbon dioxide budget. That means figuring out the most energy-efficient way to get something done. And wise use of the car is a good place to start.
We can plan our trips so that we do many things in one trip. We can ride our bikes, we can walk. Kids have a lot of power.
Try using a pump for your hairspray. Replace less efficient lights and appliances with more efficient ones to reduce your CO2. The 3 R's of a CO2 budget are reduce, reuse, and recycle.
Recycling is so important. It not only reduces the amount of garbage, but it reduces the amount of energy that we need to make all of these things in the first place.
In the United States, we've designed a lot of waste into our style of life. People in Japan and Germany use only 2/3 as much energy as we do to produce the same lifestyle. So we can design and plan pollution out too.
That's the wonderful thing about doing living lightly kinds of practices and helping to save the earth, is we discover things that are neat for ourselves.
Can you list some of the things you can do to reduce the climate-changing gases you use and produce? The worksheet answers are: we can pump it, use pump sprays, walk it or bike it to reduce our car use, replace it and improve the energy efficiency of our homes and appliances, and recycle it to live lightly on the earth. Our thanks to the staff here at the Weather Center and to all the people who helped us with this series. One final thought. When things burn, they don't disappear. Their forms change, often to gases that are putting us in the middle of a global experiment that may change life on the planet dramatically. We need to remember, we all live downwind. I'm Mike Fairborn from Weather Center 4.